Hi everybody, welcome back to another video. In this video we're starting 7.4, which has to do with dividing rational expressions. Last time we looked at multiplying them. For dividing them, let's first consider a couple of different expressions. Let's first consider the cube root of 27 over 8. If we were to compute this, we would see that the top is 3 cubed, because 27 is 3 times 3 times 3, and the bottom is 2 cubed, because 8 is 2 times 2 times 2. So notice I'm expressing 27 and 8 as perfect cubes first. Then there's a property of exponents I can use here, that this is the same thing as 3 halves all cubed. So I'm taking, because each of the numerator and denominator raised to the power of 3, I can just group the entire fraction and then raise the whole thing to the third power. And then again, this is nice because we've got the 3 and the cube root canceling. So you got the power of 3, a cube root, those cancel, and you just get 3 over 2. Awesome. So we've computed one radical expression. Let's compute one more. Suppose we take a look at, instead, this one's going to be probably a little simpler, the cube root of 27 over the cube root of 8. Now, we just compute the top, compute the bottom. The top gives us 3, as we know from before. The bottom gives us 2. So notice that we got the same answer when computing this and this. So that implies that perhaps, well, I guess it does definitely imply that these two are the same. So there's some rule happening here, and we can capture it. It's called the quotient rule for radicals. So more generally, it's panning down here, keeping this within view, but more generally, it's the case that if you have the nth root of a over b for real numbers a and b, and where b is not equal to 0, then we end up getting the nth root of a over the nth root of b. You can split up this into two radicals, one for the top and one for the bottom. So let's go ahead and take a look at some more examples to get us used to applying this rule and calculating these things. Let's say we've got the cube root of 27 over 125. Let's pan over here. Zoom out a little bit. So we want to calculate the cube root of 27 over 125. Well, we can use that rule. This is the same thing as the cube root 27 over the cube root of 125. We know the cube root of 27 from before, that's 3, because 3 times 3 times 3 is 27. And then if we took a wild guess for what the cube root of 125 is, it's 5. So 5 times 5 is 25. 25 times 5 is 125. So we end up getting 3 over 5 for the cube root of 27 over 125. Again, we just use that quotient rule down here for radicals to give us this. Let's look at some more examples. Let's say we've got the square root of 25 over y squared. So we're going to go ahead and assume that y represents a positive, or rather a non-negative, well, yeah, y represents a positive variable. So we can just basically just take the principal square root. We don't have to worry about negatives or plus or minus signs or absolute value. We don't worry about all that. We just take the square root of the top the square root of the bottom. The top we just get 5. The square root of 25 is 5. The square root of y squared we'll just say is y. We don't say the absolute value of y or anything like that in this case. We'll just assume y is positive. Next, let's take a look at some examples that involve some more simplification along the way as we calculate and apply these properties. So let's pan down and take a look at, let's say we want to calculate the square root of 80 divided by the square root of 5. Suppose we're given this. Well, from the rule that we developed right here, what we've got looks like the right-hand side of it. So maybe I'll box this for reference. So what we've got right here, this is an 8, what we've got looks like the right-hand side of this equation, but we can actually take it and transform it into the left-hand side. We can write this as the square root of 80 over 5. Now we just have to calculate what 80 over 5 is. I believe it's 16. So we take the square root of 16 and we just get 4. So that's our final answer on that problem. Let's see another. Suppose we've got the cube root of 32 over the cube root of 2. Well, here's how I'll think about it. We can just apply that rule again. This is the same thing as this. Writing it as a single radical. Then we can divide. And now we've got the cube root of 16. Notice the cube root of 16 is not 4 like the square root of 16 is. So we need to, what we need to do is we need to think of perfect cubes which would divide into 16. Well, the only useful one is 8. It's 2 cubed. So we can re-express 16 in the following way. We can write it as 2 cubed times 2. Or if you like it better, 8 times 2, whichever you prefer. Now this is the same thing as the cube root of 8 times the cube root of 2 the cube root of 8 is 2, so we get 2 times the cube root of 2. Awesome. So now, before we, just to wrap up the video, I'd like to take a look at what's called rationalizing a radical expression. So often it's called rationalizing the denominator, but you could also rationalize the numerator. You could rationalize either, but typically in practice you'll just mostly be rationalizing denominators. It's a good skill to have. So let's do that. It's a good little trick that comes up later in some places in later math classes. But anyway, let's go ahead and take a look at something like 1 over the square root of 2. And let's suppose that we don't want to have this radical in the denominator anymore. So we want to, I'll type this, rationalize the denominator. So if that's our goal, to rationalize this denominator, we want to get that that radical out of the denominator. We want to make it rational in the denominator. We can take the top and bottom of this fraction and introduce a factor of root 2 in each. So we get top and bottom multiplied by root 2 over root 2. Notice root 2 over root 2 is just equal to 1. So we're performing a perfectly legitimate operation here. We're just multiplying by 1. Now in the top we've got 1 times root 2, that's just root 2. And then think what happens in the bottom. Well, you've got the square root of 2 times the square root of 2. We know that in that situation the square roots cancel and you're just left with 2. So notice we've ended with something where the denominator is rational, and that's why it's called rationalizing the denominator. So that's a fairly simple example. We want to take a look at some more complicated examples of that sort, but before we do that, let's take one more simple one. Let's say we've got the square root of 7 over 3 written like this. And suppose we've got the same instructions, rationalize the denominator. That's what we're here to do for this problem. Well, we can write this as the square root of 7 over the square root of 3. That's the first natural step, to split it up into 2 pieces. And now we want to get rid of this root 3 in the bottom. We want to rationalize it. So to do that, we can just multiply by root 3 over root 3. And then in the top we can multiply within the radicals, because that's the product rule for radicals we learned about last section. So we get root 21. And then in the bottom, the square root of something times the square root of that same thing is just that thing. So the square root of 3 times the square root of 3 is 3. So there we've rationalized the denominator for this problem. Now I want to draw our attention to one that's more complicated. So this one is going to involve cube roots, and the process by which you rationalize the denominator is a little bit tougher, but it's not too bad if you think of the underlying principle at hand. So let's consider the cube root of 5 over 16. Okay, well, we can split this up. So that's the first thing I'll do, is I'll take this and I'll split it up into its 2 components. The cube root of 5 over the cube root of 16. Somewhere before in this, we looked at the cube root of 16. What did we get? This is something that doesn't get stressed in math classes often enough, and that's that you should reuse the results you've already developed. You shouldn't be recomputing things you've already computed once. So we earlier established right here that the cube root of 16 is just equal to this, which is equal to this, which is equal to this. So the cube root of 16 just equals 2. So maybe I'll fill that in now. It's 2 times the cube root of 2. Again, that's from right here. I'll use a different color to emphasize that. I'll just box it in red. Okay, so that's from there. And now the top is still the same. It's just the cube root of 5. And remember our goal. Our goal is to rationalize the denominator. So we need to take this and multiply the top and bottom by something. It's still that same idea. We're still multiplying by 1, but the question is, what do we multiply the cube root of 2 by in order to give us a perfect cube? That's what we'd like. We'd like to have, actually let me select this and copy this. Yeah, go. I want to take this down here. So we want to rationalize the denominator by multiplying the top and bottom by the same thing, but the question is, what is that thing? What's going to get rid of the radical in our denominator? What's going to rationalize that denominator? So we need to get a perfect cube. Ultimately, we need the easiest way to end up with a perfect cube. Well, we've already got the cube root of 2. It'd be nice if it were the cube root of 8. If it were the cube root of 8, then it would simplify and it would be rationalized, right? So here's what we'll do. We'll take the top and bottom of this thing and multiply by the cube root of, well, how many more 2's do we need? We've already got 1 2, right? Well, we need 3 2's. So what I'll do is I'll just multiply the top and bottom of this by 2 squared. If you think about it, we originally had 1 2 in the denominator, and after doing this, we're going to have 3 2's. 1, 2, 3. So that means that at the end of the day, the cube root of that product will simplify nicely. So this is going to be, I'll write this out in multiple steps, the cube root of 5 times the cube root of 4. And then here we're going to have 2 times the cube root, we're using that product rule again, 2 cubed. So we just multiplied the cube root of 2 times the cube root of 2 squared. And now we'll use the product rule in the top. That gives us the cube root of 20. And then in the bottom, the cube root of 2 cubed is just 2. So we've got 2 times 2, which is the cube root of 20 over 4. And the question is, can we make this look nicer? Probably. We probably could do one more step, but I'm okay with this. So our ultimate goal, remember, was to rationalize the denominator, right? So that was our goal, and that's what we ended up doing. We don't have a radical in the bottom anymore. We have made the bottom a rational number. So that's it for this video. In the next video, we're going to look at how to combine and simplify expressions, radical expressions that contain multiple terms. So anyway, that's it for this video. I hope you all have a terrific weekend, and I'll see you in the next one.